Today we are going to be evaluating limits algebraically, evaluating one-sided limits algebraically, and evaluating limits at infinity algebraically. So to review, I'd like to take a look at our one-sided limits graphically. So if we are approaching 2 from the right, I don't know why that's a little blurry. If we're approaching 2 from the right of this function h of x, 2 from the right would be coming at 2 from here, right? So the function is up here. So from the right we are approaching 4, so the limit is 4. 2 from the left, the function is approaching 3, so that limit would be 3. So the limit, since these are not the same, this limit would be non-existent, dne. What is the function value at 2? The function value at 2 is 3. Let's approach -2, this time from the left first, so we're approaching -2 from the left. The function value is, from that side, the function value is approaching -2. -2 from the right, the function value is up here, it's approaching 3. I think there's a little typo there. There shouldn't be a plus, that should just be a regular 2. So the limit as x approaches -2 would be, does not exist, it would be non-existent. The function value at -2, the function value at -2 is this point right here. It's at 1. Piecewise functions can do funny things. Okay, as x approaches -infinity, as x approaches -infinity, so x is going to -infinity, where's y? What is y doing? Well, y appears to be going to -infinity. That is a special dne. Does not exist. What about when x approaches positive infinity? As x approaches positive infinity, the function value is going also to -infinity. Non-existent. Okay, so there is no horizontal asymptote that would make this limit of these limits of infinity, limits at infinity, it would make them go to a real finite number. Okay. So one-sided limits are very obvious when a graph is provided. When you want to or need to do a one-sided limit of a function whose equation is given rather than whose graph is given, it can be more difficult. So here are some helpful tips. First, just try to plug in the number as you would any limit. Okay? If you do not get 0 in the denominator, and you get a real number, not an indeterminate form, then that is your answer to the limit. So 2 from the right, we're going to begin by just plugging in 2 for x. We would get 4 minus 4, which is 0. On the bottom we would get 4 plus 4, which is 8. 0 divided by 8 is not indeterminate, that is 0. So this limit is just 0. I wrote it over here because I was wondering if I was going to get a 0 in the denominator as well, but I didn't, just got an 8. So that whole thing is just 0. Okay, let's plug in, I know that this is a one-sided limit, but let's just plug in 3. 4 minus 3 is 1. If we plug in 3 there, we're going to get 27. That is just 27, 1 over 27. Nothing funny going on at all. Yes, it's a one-sided limit, but it behaves just like a regular limit. Okay, x is approaching pi over 3 from the positive side, so from the right. Sine of pi over 3. Sine of pi over 3 is square root of 3 over 2. Cosine of pi over 3 is 1/2. I would multiply top and bottom by a 2. And this would get me square root of 3 on top, 1 plus 2 on the bottom, square root of 3 over 3. Okay, so that is all well and good. It's nice, but most of the time it's not going to be that way. Most of the time you are going to get a 0 in the denominator. And sometimes you'll get an indeterminate form. If you get an indeterminate form, you just do the same techniques that we learned the past 2 days. So factor and reduce, complex fraction, multiply by a conjugate, those all remain for those. But for one-sided limits, quite often you'll get a 0 in the denominator, but not a 0 on top. Okay? So let's take a look at what happens here. So here we have 3 coming from the positive side, and there is no hole. There's no hole here. Okay, if I put 3 up on top, I get a -2. If I put 3 on the bottom, I get a 0. Okay, this is one of those where I have an asymptote. There's a vertical asymptote at x is equal to 3. There's a vertical asymptote there. Okay, I know my curve is either going to go to positive infinity or negative infinity. I just don't know which one. Okay, so let's take a look at how we can figure out which one. Okay, so let's take a look at that. Same one. Okay, and what I just said in words is what I wrote right here in your notes. So same function. Okay, so if I'm coming at 3 from the right, okay, and there's no hole, I get 0 on the bottom but not 0 on top, so there's no hole. I know there's a vertical asymptote. Vertical asymptote at x equals 3. So I know my answer is going to be either positive or negative infinity. I know it will be. I just need to find out which one. To find out which one, we are approaching 3 from the right. We're approaching 3 from the right. So let's plug in a number that's close to 3, but on the right side of 3. So what number is on the right side of 3 that's close to 3? And don't say 4 because that's a little bit too close. Or I mean, that's not close enough. Sorry, that's not close enough. How about a 3.1? Let's plug in 3.1. Okay? Or maybe 3.01, or maybe 3.001. So just something very close to 3, but to the right of 3, so just over 3. If I do that, on top, this is still approaching -2. Nothing's going to change that. It's going to still approach -2. On the bottom, I'm getting rid of my equal to sign here for a second. Okay, so when on the bottom, 3.001 minus 3. It is a tiny number, but it's positive. This is tiny, but positive. Close to 0, but positive. Okay? I have a negative divided by a positive. So this is going to be, this limit will be negative infinity, which is a special kind of does not exist, non-existent. So ask yourself, what sign will that be? When I put a number close to that, but on that side, what sign will this be? And then evaluate your signs. A negative divided by a positive will give you a negative. On a multiple choice answer, that would be the correct choice. Okay? On a multiple choice answer, they would not have both of those as choices, only one of them. All right, we're approaching 4 from the left, and notice this is completely factored, and there is no hole. No hole, asymptote. We have an asymptote when x is 4. So I know my answer is going to be either positive or negative infinity. I know it will be. I just need to find out which one. To do that, we evaluate the signs. So I'm going to plug in a number close to 4, but this time it will be on the left of 4. So I need a number close to 4 but on the 4's left, like 3.999. Okay? If I do that, this is still close to 4, so that's still going to be a negative 1. This is going to be a positive 6 on the bottom. If I put this in for x, yes, it's going to be close to 0, but it's going to be negative. So it's going to be tiny but negative. So again, I have a negative divided by a negative, so this will give me a positive infinity. Positive infinity. Okay, let's do another one. We're approaching 2 from the positive side, and I look here. 2 from the positive side is going to make this piece 0. It's fully factored and there are no holes. So up on top, I'm not going to get a 0. If I plug in 2 on top, I know I'm not going to get a 0 because there's nothing up there that's going to make it a 0 when I put 2 in for x. So if I do put 2 in for x up here, I would have a 2 times a 9. 18 on top, 0 on the bottom. Okay? I know my answer is going to be positive or negative infinity. So I plug in something slightly larger than 2, maybe 2.001. Up on top, we still have 18. We still have 18. Positive 18. On the bottom, we have a positive 3 times 2 minus 2.001. That's going to be tiny, tiny but negative. So which infinity is it? Negative infinity. So that's how you do a one-sided limit algebraically. Okay? Now I will say, sometimes you can actually, you know the graph. So I know what the graph of y equals 1 over x looks like. It does that. That's my base parent function, rational parent function. I'm approaching 0 from the left. 0 from the left is negative infinity. So I know that this is negative infinity just by knowing the graph. So if you know the graph, that might be a good way to do it, because limits graphically make a lot of sense. It's very visual. And again, if you get an indeterminate form when you do a one-sided limit, you have to go and do the techniques that we have been looking at the last couple of days. Okay, factor and reduce, complex fraction, multiply by conjugate. All right. Also today we're going to take a look at limits when x is going to infinity. When x is going to infinity, you have a rational function like these. You only need to consider the highest degree term in the numerator and the highest degree term in the denominator, and then reduce. Okay? And here's why. As x approaches infinity, or negative infinity, in this case, the cubic is the highest term on top. The cubic is just going to rule. These have little effect as x goes to infinity. So these can be ignored, totally ignored. In the bottom, the highest degree term is this 5x cubed, so we can ignore anything else. So this is the same thing as this limit. 4x cubed over 5x cubed. That's the same thing as that limit. These limits are equal. Okay? What can we do with these x cubes? We can reduce them. So this is the limit of, as x goes to infinity, of 4 over 5. Well, we lost our x's, so our limit is just whatever is left, 4 over 5. So that limit is 4 over 5. You can only do this when x is going to infinity or negative infinity. You can only ignore things when x is going to infinity or negative infinity. Okay, for this one, I see x is going to infinity, so I know I'm going to ignore some things. I'm looking for my highest degree term on top. I'm looking for my highest degree term on the bottom. I'm going to write those down, and then I'm going to reduce. So how do x to the fifth and x cubed reduce? Well, they reduce leaving an x squared on top. So this is negative 2x squared divided by 7. Now, I'm thinking of what happens to this as x goes to infinity. As x goes to infinity, the numerator, x is going to infinity, but I have this negative 2, so what is that numerator going to? That numerator is going to negative infinity. So we have something going to negative infinity divided by a positive 7, so this whole thing is negative infinity. Okay, one last one. Alrighty, x is going to infinity, so I know I need to go to my highest degree term on top and my highest degree term on the bottom. I'm going to ignore everything else and simplify those. So we have a 1 on top and a 7x on the bottom when we simplify those x's. Okay? Now we let x go to infinity. Well, x is going to infinity, so the denominator is going to infinity. 1 divided by something going to infinity is all going to 0. Infinity on the bottom, it goes to 0. Okay? And that is limits when x is going to infinity. That's how you handle those. And we will do more with that later in calculus.